Thanks, everyone. Hi, so I'm Ihor, and I'm an OS engineer at Crichton. And at Crichton, our goal is to build a platform for connected industrial devices, secure and reliable platform for industrial devices. And so in this talk, I'm going to talk about why seL4 is a good basis to build these devices with in Beam on top of seL4. Now, I gave slightly different version of this talk a couple of weeks ago at the seL4 summit, where my goal was to convince the seL4 people that running Beam on top of seL4, that using Beam. I gave a version of this talk where I was trying to convince the seL4 people that running Beam on top of seL4 was a good thing and it was a good development environment for that. So today I'm going to flip that around and I'm going to try to convince the Beam people that running seL4 underneath the Beam is a good idea for building secure and reliable systems. All right, so yeah, what I'm going to talk about is basically what does it mean to have a secure and reliable system? Why is Beam good for that? Why is seL4 good for that? And then talk about some of the challenges of actually making that happen and what we've done to make that happen. Okay. Now it works. So as I said, our goal is to develop a platform, an OS platform for connected industrial devices. These are also called industrial IoT, industrial control systems, OT, and so on. And what it means is basically devices that control industrial systems. So things like factories, things like agricultural systems, things like energy generation and distribution systems, and so on. So we're talking about kind of the smart devices that control these machines that run these systems. And there's a couple of important things here. One is that they're connected, which means they're connected to a network. And the goal of that is to extract data from these systems so you can do data analysis on them, to monitor how these systems are doing, how the machines in the systems are going, how the devices are going, so that you can have insight into what's happening, whether you need to make any changes or not. And then also to be able to remotely control these systems as well, right? So these devices have a lot of responsibility. The other thing is that they're often high value. So the task that these devices do is often worth a lot more than the devices themselves. So it's really important that the devices work well, they don't crash and so on, because otherwise it's going to be very expensive. And the last thing is that downtime can be very expensive in these systems. You know, taking a factory down for a little bit means you're losing a lot of money. So downtime is really expensive. In some cases, it can also be actually dangerous, physically dangerous, right? Think about reactors and stuff like that. So this is the context. And we're trying to build kind of systems that will allow us to have these connected industrial devices without the problems of downtime and so on. Right? So that's the context. And in order to have those kind of systems, we need to have security and resilience. So security means that the systems, the devices, are robust in the face of attacks. So if any kind of malicious party comes in and tries to attack these devices, tries to get in there and make them do things they're not supposed to do, it needs to be robust in the face of those kind of attacks, so it doesn't succumb to those kind of attacks. Which means we need to have protection at all the levels. We need to have protection in hardware, in the system software, in the application software, and even in the services that they connect to in the cloud or whatever as well. So protection is really important. We don't want people coming in and disabling the systems. We don't want people coming in and stealing the data that the systems are producing. We don't want them coming in and controlling the systems and making them do bad things. So security is very important. And resilience is also very important. This is being robust in the face of faults. So things that accidentally happen, that break, it needs to be robust when faults happen. So this means things like, if something bad happens, the system needs to be able to heal itself. It needs to be self-healing. It needs to be able to recover. If it does go down, it needs to recover very quickly. Minimizing downtime is very important. As I said, downtime is expensive and potentially dangerous. Both security problems and resilience problems can lead to this downtime and other worse things. So if we want to have a platform for these connected industrial devices, it needs to be secure and it needs to be resilient. And this is very important. And in order to achieve this kind of security resilience, there's three things that we need to be able to do. We need to prevent vulnerabilities from being exploited. We need to prevent faults from occurring. And a lot of that comes down to, if we're building software systems, is writing good software. making sure that we don't have vulnerabilities in our software, making sure that we can deal with faults that occur and so on. So we need to prevent bad things from happening. We do the best job we can to do that, but eventually bad things will happen. And so we also need to contain bad things. So we need to stop attacks from propagating throughout the whole system. We need to stop faults from propagating throughout the whole system. So if part of the system is attacked, some of the software is attacked, we need to limit the effect of that to where that vulnerability is that's being exploited, and not let that kind of go on to the rest of the system and take the whole system down. So we want to limit the effect of any problems. And then we need to be able to recover. So we need to be able to restart any of these faulty or exploited components so that the system keeps running. We don't want an attack or a fault to happen and bring the whole system down. So we need to be able to quickly restart anything that's broken, get it working again. We need to also be able to fix those problems, right? If there is a vulnerability in the code, we need to find that. We need to be able to fix it. We need to be loaded up again and keep the system running without bringing the whole thing down. So 3 important things: prevent, contain, and recover. I'm going to talk about how we can use Beam and seL4 to achieve these 3 things. So everyone here should know what Beam is. Beam and its related languages, Erlang, Elixir, and so on, and the frameworks are really good at helping us prevent problems. Right? So the languages and the OTP features steer us towards writing better code, better structured code, building systems so that they don't have as many vulnerabilities or problems and dealing with faults and so on. The isolation and memory safety that's inherent in having all these processes running somewhat independently and communicating and so on helps us also prevent problems within the Beam. And then the concurrency model helps us avoid a lot of concurrency problems. So a lot of classic kind of problems with security and so on happen through concurrency. So if we have a good concurrency model, we can build good concurrent systems. We can avoid a lot of those problems. And so that helps us prevent the problems, right? Prevent vulnerabilities from being in the code and being exploited, prevent faults from causing bad things. And the other thing Beam and the associated environment helps us do is recover from problems. So we've got linking, monitoring, supervision trees, and so on, the kind of let it crash philosophy where if things do break, we know how to restart it. Our systems are built such that things can be restarted. We can recover from problems very quickly. And then, we can fix the code. We've got dynamic code update and things like that. So Beam's also really good at the recover part. But what we don't get is the contain part. So if something bad happens within a process in the Beam, that essentially can take down the whole Beam if it wants to, and potentially go on to other processes as well. So what we have is seL4. So most of you are probably not familiar with seL4, so I'll introduce that a bit and explain why this is the missing part. So seL4 is an operating system microkernel. It's capability-based security, which means that you have fine-grained control over resources and access control to resources and who can access what. And it's formally verified, which means there's a mathematical proof of how it works and its correctness and so on. So I'll talk more about that in detail later. But ultimately, what all of this together means is that seL4 provides us a platform that gives us proven isolation between processes. And that's what gives us the contain property. So it allows us to build our systems such that we have a bunch of separate processes, not Erlang or Beam processes, but this is operating system processes. And when things break in one of those processes, it gets contained within that process. So this kind of isolation and containment of problems within processes is kind of what an operating system is supposed to provide you. And there's a lot of operating systems out there like Linux, Windows, and so on. So why am I claiming that seL4 is special? Well, there's 2 reasons. One is that it's a microkernel. So I'll talk about what that means and why that makes seL4 special and better at providing this containment. And then the other one is formal verification, which I'll talk about afterwards. So the best way to explain a microkernel is kind of why a microkernel is good is to explain what isn't a microkernel and why that's not as good. So traditional operating systems like Linux, Windows, and so on are based on a monolithic kernel. What that means is that all of the operating system functionality like your file system, like your network stack, like your device drivers, like your memory management, and so on, are all running in the kernel mode of a processor, so the protected or privileged mode. And what that means is that any of that code running in kernel mode can do anything it wants in the system. It can access any memory it wants, it can access any hardware it wants, it can manipulate the whole system and all the processes running on it, and so on. So it's very privileged and can do whatever it wants. Now, in a monolithic kernel, so traditional operating system, all of this code runs in kernel mode, and that's tens of millions of lines of code that's running in this privileged mode. And we all write software, and we know that software has bugs, and the bigger the software is, the more bugs it has. So that means there's potentially a lot of errors in those 20 million lines of codes, and those can lead to vulnerabilities. And so that means there's a lot of potential vulnerabilities running in this privileged mode of the computer, which is not great, and it breaks any kind of isolation promises that OS makes. It increases the attack surface and allows attacks to spread. So microkernels are kind of the opposite of the monolithic kernel. The idea with microkernel is that there's a minimal amount of code that's running in this privileged mode of the processor that can do anything it wants. Really, the only code that runs in there is code that can't do what it needs to do outside of privileged mode. And so we're talking about the order of 10K lines of code. Right? So there's several orders of magnitude less code running in a microkernel. And then everything else that's a traditional OS service, like network stacks, file servers, file systems, drivers, and so on, it runs as processes on top of that in non-privileged mode. And so if anything goes wrong with any of those pieces of code, well, it's limited in the damage it can do. It can't write to any memory. It can't write any memory it wants. It can't write to any hardware it wants, and so on. So it's limited. So we've got that. So we've got fewer errors, potential errors in there, a lot less code. It's more amenable to actually checking the code and making sure there's no errors. There's the isolation of the OS components. And so in general, a lot less severe vulnerabilities possible with the microkernel model, which is good, because that gives us better containment property than a monolithic kernel does. So that's the first reason why seL4 is good. It's a microkernel. The second reason why it's really good and gives us a really good containment property is that it has formal verification. So what that means is that the code of the kernel has been formally or mathematically proven to actually implement the specification of it. So seL4 has a formal specification of its API. So that is a specification written in higher order logic, so a mathematical logic, that says what every API call does, how it affects the overall system. So it has some preconditions, the API is called, and then some post-conditions. So you know exactly what the API is supposed to do. So this is written in a formal logic. And then we have proofs about that specification. So there's three important types of proofs that it has. The first is that the C code refines the specification. So the kernel is not written in higher order logic, it's written in C, right? A programming language, low-level programming language. And so we want a proof that says, well, what we've implemented in C is exactly what is specified about the API. And so we have that. We have a mathematical proof that takes a mathematical representation of the C code and proves that it does exactly what the specification says it should do. Nothing more and nothing less. That's important because A, we know that it's correct, that it does what we want it to do. But we also know that it doesn't do other things that we don't want it to do. For example, buffer overflows or integer overflows or other types of code bugs that produce vulnerabilities. So we get those two things from that. It does what it's supposed to do, but it also doesn't do what it isn't supposed to do. So that's nice. Typically, when we talk about this, people raise their hand and they say, well, there's a couple of problems with that, right? First of all, you're verifying C code. But that's not what's running on your computer, right? Your code gets compiled into binary, and that gets executed by your processor. So what if the compiler is introducing faults in there? So that's the first thing people complain about. So we have a proof that the binary implements the C behavior. So we take the binary, we have a representation, a mathematical representation of what the binary does. we have that C representation, and we can prove that the binary does what the C does. And so if you combine those two, you can now say the binary does what the specification does. And so you've got this proof going all the way down to the binary. The other thing people complain about or ask about is, how do you know the specification doesn't have any bugs, right? You may have implemented that specification correctly, but if the specification is wrong, you still have a broken implementation. So the other thing that's been done is that there are proofs about the specification. And the thing we want seL4 to do, and the thing we want the specification to do, is to give us this containment, this isolation. And so we have some properties of what we mean by isolation, and those are things like confidentiality and integrity and so on. So that if you've got two processes running and they're separated from each other, process A can't get data out of process B. That's confidentiality, and the opposite is, integrity is that process A can't change the data in B. Those are the properties we want for a secure system. And so what has been done is that these properties have also been specified in a higher order logic, and then we have proofs that the specification, that the mathematical specification implements those properties. And so now we have a proof saying that seL4 gives you these confidentiality and integrity properties all the way down to the binary, which is amazing. So these two things, the fact that it's a microkernel already small and provides us isolation, and then that the isolation is guaranteed, gives us a really strong guarantee that we can provide this contains property. But it's not a silver bullet. You still need to do work. And the work that you need to do is you need to develop and design your system properly to take advantage of what seL4 gives you, of these properties that seL4 gives you. So I'm going to walk through a really simple example of how you might build a system and take advantage of those properties. So we're going to look at kind of just the architecture, how we would build a simple weather station. This takes information from a sensor that gives you like temperature, pressure, and so on, and provides a nice UI for that, so it shows you kind of what the current temperature is, and allows you to potentially do some control over that system. So what do? We choose some hardware. We run seL4 on that. So this is all running on one system. And then we need to get data from a sensor. So we write our kind of weather sensor program as an Elixir program running on the beam. This has kind of a sensor driver. It gets data about the current temperature, the current pressure, and so on, and collects that. It obviously needs to talk to hardware to do that. So we add a C driver, a driver implement in C that's an I2C driver. So this beam talks to the I2C driver to actually connect to the sensor and get the data out of that. We want to display that as well. What we don't want is to run the UI software in the same process as the sensor software, right? There's no reason why the UI should be able to talk to hardware directly. So we want to separate those. So we start up another beam, and we have the weather station UI in there. So this is a scenic UI. It provides kind of this nice screen. It gets data from the weather sensor, interprets that, and makes a nice drawing of that. In order to display that, we need to go out over the network. So this is a remote display. The weather sensor doesn't have its own screen. So we need to get a network driver, so we add a network driver in there. We don't want our communication, our data to just go kind of plain text over the wire. So we add a little encryption tunnel there, a VPN tunnel there as well as a Rust component in this case, and then the weather station needs to talk to that. So each of these boxes is a separate seL4 process, right? Okay, so then we've got basically our weather station. One of the things we also want to be able to do is have some kind of admin control over the machine. So we add another Elixir process that is an admin process that also talks over the network, over this tunnel, and allows us to control the device. So allows us to restart the device, upgrade the software, and stuff like that. All of these are separate processes. And because we're running on seL4, we have some guaranteed isolation between those processes. So for example, if someone figures out a vulnerability in the scenic remote UI kind of protocol and gets into this weather station UI and takes over that component, well, that component, it can play around with the display, but it's not going to be able to drive the device. It's not going to be able to do bad things to your sensor, for example, or access the I2C bus and any other devices on that. it's also not going to be able to send commands to the admin component to restart the device or change the software or anything like that. Right? So we've got this isolation there. And this is very important in building systems on top of here, is to get that isolation right. And then you can take advantage of what seL4 gives you and the guarantees that seL4 gives you. So that's what we want. What does it mean in practice? How do we get there? Well, the minimum thing we need in order to be able to develop for seL4 in Elixir, right, to write Elixir programs that will run on seL4 is we need Beam running on seL4, and then we need to have this communication from the Beam to different seL4 components or other Beams running on seL4. And then usability bonus is we'd like to have libraries that wrap this communication so that it makes it nice. We'd like to be able to use Elixir to actually define the system, all of these components in the system, to build it and have, use the existing build system like Mix to be able to actually build all of this stuff. I'm going to talk about these two things today. So how Beam on seL4 and the communication. So running Beam on seL4, I'll be brief about this because my colleague Kent is going to talk a lot more about this tomorrow. Basically, getting Beam running on seL4, we've got Beam running as a single seL4 process. In order to make it work, it relies on a bunch of POSIX functionality, which is not something that seL4 natively provides. seL4 is a microkernel, so it provides a very minimum OS functionality, nothing resembling POSIX. And so in order to get Beam running on seL4, we essentially need to implement the basic POSIX functionality that it needs on top of seL4, which we've done. So kind of p-threads wrappers around the native threads, a basic file system, some POSIX system calls, and a network stack, LWIP as a network stack. And then we also have to provide a bunch of OS processes for other services, potentially shared services that it needs. Things like access to a clock, device drivers, things like access to serial, Ethernet, and so on. But also a logging functionality, a random number generator functionality, and so on. So by providing these things, we get Beam running on seL4, and then we can run multiple instances of this Beam. And we don't actually need to touch the Beam code itself, for the most part. So that, Kent will talk to you more about kind of what the challenges are of that and doing that. And the other thing we need to do is communicate. So the first thing we have is we want our Beam processes to be able to communicate with native C components, for example. So we had an example of the weather sensor talking to an I2C driver that was a C component. So how do we get that working? Well, we take advantage of the inter-process communication mechanisms that seL4 provides, as well as shared memory. And we implement kind of an seL4 port driver or a NIF in our Beam to be able to invoke those system calls. So we do that work, and now we can do direct seL4 calls to talk to other components. And our configuration of seL4 limits which components we can talk to and how we can talk to them. But this basically does that. Now, this works well, but it doesn't, it kind of breaks whatever communication abstractions that Erlang or Elixir or the Beam provide us, right? It's not using the message passing that Erlang and Elixir provide. So the other things we can do is we can actually take advantage of the distribution protocol and have communication between Beams using that distribution protocol, so actually sending Erlang Elixir messages and so on. So one way of doing that is using the existing TCP/IP distribution protocol and the network stack we have, and then we provide a simple kind of local network driver. It's not really a network driver, it's really just kind of a loopback driver to be able to send messages to other Beams running on the same seL4 instance. So this is a very straightforward way of doing it. It's a little bit heavyweight in that you've got a network stack and so on just to do local communication. That's not really necessary. But this means we don't have to change anything about the Beam at all. We just add our little component here, and the communication happens. And now we can use all of the distribution protocol as well as code that builds on that Elixir, OTP, Erlang, and so on provide us. And we can make use of all of the tools and libraries and so on that have that. The other cool thing we can do here is we can take this network server and we can add some functionality to that. For example, a filter. So we could add a filter and take a look at what's actually being sent across and limit what we can send across. So we don't want this beam to be able to send an exit command to the other one to run some code that runs that. So we could potentially limit that by running a filter and examining what's being sent across. All right, I'm being given time. So almost done. So we can improve that by taking advantage of some native seL4 inter-process communication and essentially writing kind of our own distribution protocol carrier using our port driver or NIF to do native communication between beams as well. This takes away that heavy weightedness of the network stack, of having the extra component there and so on, but still gives us the flexibility and gives us the option of also still putting a filter in between there as well. So 2 ways of doing that communication. So this brings me to the end. Kind of what have we done? Well, I've told you we need this prevent, contain, recover properties to get security and resilience, and we want this for these connected industrial devices. Beam is really good at giving us the prevent and recover part. seL4 is really good at giving us the contain part, so we should be building systems, beam systems on top of seL4 if we want to put them in situations where we need really secure and reliable systems. And so we've done a bunch of that work, porting beam, getting communication working, and what we're currently working on is getting all those usability bonuses as well, having a really nice Elixir-based environment for actually building these systems. Thank you.